Hey guys, I'm sorry it's been a while since I made one of these videos, but today we're gonna move on with topic 10, which is oscillations. And this is a topic that, from my experience, creates lots of confusion to students, so hopefully things will be clear from my side at least. So what are oscillations? Oscillations can occur when a restoring force, and I'm going to explain in a while what a restoring force is. So when a restoring force keeps bringing an object back to its equilibrium position. Okay, so it's easier to see this through two examples, which happen to be the examples that you need to understand for the A-level test. So the first example is the spring. Okay, so let's say that we have a wall, something like this, and there is a spring attached to the wall, and and what's going on? Okay, I made it. And there is an object attached to the spring, so let's make it red maybe. All right, so let's say that this is the equilibrium position. Okay, so this is the equilibrium position, and what's gonna happen if we pull it? So let's turn a clean page, and sorry, I'm losing my colors today. So if we draw again the spring, this was the equilibrium position. Let's say that we pull the spring like that, and the object moves by some distance x. Okay, then as we know, there will be a force F that happens to be proportional to the displacement from the equilibrium position. So this is the equilibrium again, and the negative sign denotes that it's gonna tend to move the object to the left, so it's gonna pull it back towards the equilibrium position. Okay, so this is the spring example. Now let's turn another clean page and see another popular example, which is the pendulum. Okay, so let's say that we have a ceiling and we have a pendulum. Okay, something like that. Okay, this is the equilibrium position, so that's the equilibrium. Okay, and let's say that we pull it by an angle theta. Okay, it looks huge here, but let's imagine that theta is really, really small. So theta is much, much less than 1. This double lesser than means much, much smaller than 1. So very, very small angle. And 1, we mean radian. So something like maybe theta is 0.1 radian. So something really, really tiny. That's like 1 degree. Okay, so if that's the case, okay, so there is a mass attached to the spring. I forgot to mention that. So what kind of forces will this mass experience? You will have gravity, of course, mg, the tension of the rope. Okay, and we can analyze gravity into two axes like that. So if that's theta, this is also theta. Okay, and the reason is that what's the reason? This line, if I extend this line is perpendicular, sorry, is parallel to that line. So if that angle is theta, that angle is also theta due to the Thales principle, if I remember my math theorems correctly. Okay, so if that's theta, that's mg cosine theta. Okay, and therefore this is mg sine theta. Okay, and this is the restoring force. Okay, this one, that's the restoring force because it points to the right towards the equilibrium position, so it tends to bring the object back. And if we call this displacement x, notice immediately that sine of theta is minus x over L. And I use the minus sign because we consider the equilibrium to be the 0. So we can draw axes like this. So this is our y-axis, sorry, and this is our x-axis. So if that's the origin, this position, this one, is minus x from the origin, okay? So sine theta is minus x over L, and we can write that F, the restoring force, sigma F actually, minus mg sine theta. Therefore, the restoring force is minus mg x over L, and notice that this is constant, okay? And I forgot to mention that L is the length of the string, okay? So that's L. So the restoring force tends to bring the object to its equilibrium position, just like with the spring, okay? Now, let's go talk about the conditions to have simple harmonic motion, okay? So what are the conditions needed to have oscillations like that, and especially simple harmonic motion? So the first one is that the acceleration must be proportional to the displacement. The second one is that the acceleration must be in the opposite direction than the displacement. And this is it pretty much. These are the two conditions. I'm sorry, I made it sound like there was a third one, but there is not. So both of these conditions, are satisfied when the acceleration is equal to minus omega squared times x, okay? And omega is the angular frequency of this oscillation. So it's the time needed for one cycle to complete, just like in the circular motion, okay? So let's go see what's going on with the spring example. So for the spring example that we just saw, F is minus kx, which means actually the sum of all forces in the x direction is minus kx, and the sum of all forces due to Newton's second law is m times a, and this is equal to minus kx. Therefore, the acceleration is minus k over m times x, which you can write as minus omega squared x if omega squared is defined as k over m, okay? So this is an example. I mean, the spring is an example of simple harmonic motion because all the conditions are satisfied, okay? If omega squared is equal to the spring constant over the mass attached to the spring. And in the pendulum example, we have the sum of all forces is minus mg over L times x, but the sum of all forces, if we apply Newton's second law, is mass times acceleration, and mass times acceleration is minus mg over L times x, and we get this nice cancellation. So the acceleration is minus g over L times x, and we can write this as minus omega squared times x, with omega squared equal to g over L. So for the pendulum, the dependency of the angular frequency, sorry, there is no mass dependency for the angular frequency of oscillation, okay? And we're going to talk about stuff like this later, but for now, so note that omega is defined as 2 pi over the period, which is equal to 2 pi times the frequency. Okay, so this is the same angular frequency we used in circular motion, but let me talk a little bit about it. So omega is the angular frequency. Okay, angular frequency, just like in circular motion. And this is because the reason why we use the same angular frequency is because the motion is repetitive with period t, capital T. Every t seconds, the object returns to its original position just like in circular motion. So if it starts, for example, here, so if this is t equals 0 and x, the displacement is 0, then in 1/4 of a period, if this is the equilibrium position, it's going to make it all the way to the right. So in 1/4 of a period, it's going to make it to the rightmost position. Then in another 1/4 of a period, for a total of t halves, is going to return to 0. By the way, it starts by moving to the right, and now it moves to the left. It's moving to the left. Okay, its displacement is 0. I will need a clean page. In another 1/4 of a period, for a total of 3/4 of a period, it's gonna make it all the way to the left. So this is 3 tau over 4 t, sorry, not tau, and the displacement is minus a, which is the maximum displacement to the left, and it's gonna be moving to the right now. And in another 1/4 of a period, it's gonna make it where it started. So in a full period, it's gonna go to the same position it started, moving to the right. Okay, and the same goes for any other position. So if it starts in this extreme position, for example, okay, in one period, it's gonna return to the same extreme position to the right. Okay, so in one full period, the object returns where it started. Now let's talk a little bit about the units used in simple harmonic motion. So the units for the acceleration, it's the usual meters per second squared. Omega is measured in radians per second. Period is measured in seconds. Frequency is measured in inverse seconds, which is also known as hertz. And the displacement is in meters. Now let's talk a little bit. It's a little bit of self-explanatory, but we're gonna talk about it anyway. Let's talk about the relationship between the angular frequency and period. To t. So the relationship of angular frequency to period. So for the spring, we found that omega squared is k over m when we discussed about this earlier, and since omega is 2 pi over tau, we can plug it in, and this is equal to k over m. So 4 pi squared over t squared is k over m. If we bring t squared to the other side, we find 4 pi squared m over k. So t is 2 pi the square root of mass over k. I think this is given in the back of the paper, but it's good to know anyway. And for the pendulum that we already studied, we found that omega squared, so pendulum, we found that omega squared is g over L. So 4 pi squared over t squared is g over L. I'm not going to go through all the math. I'm going to quote the result. T is 2 pi square root of L, the length of the pendulum, over G. Okay. Now, the next thing I want to talk about is the math of simple harmonic motion. So let's start a clean page. All right, so math. In general oscillatory motion, the motion is described by functions such as sine omega t. So the displacement with respect to time is equal to some displacement a times sine omega t, or x equals to minus a cos omega t, or x is minus a sine omega t, etc. So the reason why I use sine and cosine functions is because we have oscillatory motion, and if you recall, the sine function looks like this and the cosine looks like this. So they have oscillatory behavior by definition. Therefore, they are appropriate for discussing oscillatory motion. Okay. If you want to see why we use sine and cosine functions mathematically, you can. So why? It's the most important question in life. So let's take x to be a sine omega t. Okay. Oops. I have to do something about my handwriting, guys. I'm sorry. So a sine omega t. Then recall that a, the acceleration is d squared x over dt squared, which means that is the first derivative of the first derivative of x, which is what's the first derivative of a sine omega t is going to be omega a cos omega t, right? And if we take this derivative once again, we find minus omega squared a sine omega t. But what is this? A sine omega t? It's x. So this is omega squared x. Okay, so it works. So sine and cosine functions work. This is the reason why you use them. So which equation describes the motion? I mean, do we use a sine omega t? Do we use a cosine omega t? Do we use minus cos omega t, etc.? So which equation describes the motion depends on the initial position of the oscillator. Depends on the initial position of the oscillator at t equal to 0. Okay. It also depends on its velocity and etc. And we will talk about that in a moment. So let's see this through an example. So study of x equal to a sine omega t, which can also be written as a sine of 2 pi over t times t. Okay, so I substituted omega for 2 pi over t. So this equation 1, let's call it 1. Therefore, v is dx over dt, which means that this is equal to omega a cos of 2 pi over t times t. So this is equation 2. And if x is a sine omega t, then a is minus omega squared a sine 2 pi over the period times t. So this equation 3. Okay. Now let's form a small table which is helpful in understanding what's going on. So in one column, let's have time. In another one, let's have x, v, and acceleration. Okay. So at time equal to 0, if we go to x, we see that the displacement is 0. For v, for time equal to 0, since we are dealing with a cosine of 0 is 1, so v is omega a at t equals 0. And for the acceleration, since acceleration is minus omega squared x, and x is 0, this is 0, okay? At t equal to t over 4, if we go in here and plug in tau over 4, we will have to deal with the sine of pi over 2, okay? Which is equal to a. So in 1/4 of a period, the object is at the rightmost position, okay? Which means that this is an oscillator that initially moves to the right, okay? So sine omega t moves to the right. The velocity is 0, and the reason is that we will have, if we plug in t here equal to t over 4, we end up with a cosine of pi over 2, which is 0. And the acceleration is minus omega squared times a. For time equal to 1/2 of a period, if we plug in here, if we go here and plug t over 2, we end up with sine of pi, which is 0 again. Then the velocity is minus omega a, because if we plug in tau over 2 in the cosine, we will get cosine of pi, which is minus 1, okay? So minus omega a, and the acceleration is 0, okay? Now for time equal to 3 tau over 4, if we plug in for the time here equal to 3 tau over 3 times the period over 4, we get, what do we get? We get the sine of 3 pi over 2, right? Which is minus, 3 pi over 2, which is minus a. So for time equal to 3/4 of a period, the displacement is minus a. If we plug in 3/4 of a period into this time t, small t, okay, lowercase t. So for time equal to 3/4 of a period, the velocity is going to be the cosine of 3 pi over 2, which is 0. And the acceleration is going to be minus omega squared of whatever the displacement is, so omega squared times a, okay? And for a full period t, the displacement is going to be 0, because if we plug for lowercase t here, we will get the sine of 2 pi, which is 0. The cosine of 2 pi is 1, therefore the velocity is omega a, and the acceleration is again 0. Okay, so we have this nice little table here, which we can plot. So let's do the graphs. I'm gonna try to fit all of them into this page, which is small. Unfortunately, I have to buy a larger iPad. So you guys can donate to the channel so I can buy a larger and newer iPad, just saying. So anyway, okay, so if this is the displacement and this is the velocity and this is the acceleration, and let's do, so that's my 0, so this is time t, okay, this is 1 period t, this is half a period, t halves, and if we halve this, we're gonna get this is t over 4, and if we halve this, we're gonna get 3 t over 4, 3 periods over 4. So the maximum displacement is a and minus a. The maximum velocity is omega a. So this is the velocity, okay, and minus omega a. And for the acceleration, the maximum acceleration is omega squared a. I'm sorry, this is a mess, and minus omega squared a. So for the velocity, for the displacement, we start at 0 and we go to maximum at t equal to t over 4, and we go down there and up. For the velocity, since the displacement is 0 at time equal to 0, the velocity is going to be maximum. So let me use blue color, okay? So first of all, the object can only move from a velocity omega a to minus omega a, okay? And it starts with a maximum velocity, maximum positive velocity, it goes to 0, goes up and up there, okay? Hope this makes sense. So at time equal to 0, the displacement is 0, but the velocity is maximum and to the right, okay? And now let me use, what shall we use? Let's use orange for the acceleration. The acceleration can only move between these two extremes, and it follows the same pattern as the displacement, but opposite direction, okay? Because you have that minus sign. So this is what the acceleration looks like, okay? This is a mess. I hope it makes sense. But as I said many times, if something doesn't make sense, guys, you can let me know in the comments, okay? So some things that we can notice from the plots is that notice that v, the velocity, is pi over 2 ahead of x, and this is because the velocity is at the maximum when the displacement is at the minimum, so it's pi over 2 shifted to the right, just like the sine function, okay? And a, the acceleration is pi over 2 ahead of v, okay? And I think we covered everything I wanted to say for now. One more thing is that the gradient of x, is v, and the gradient of v is a. And we can also use the fact that a is minus omega squared times x, and this comes handy when they give us a graph. So for example, they might give you a graph of displacement with respect to time that looks like this, okay? So this is time 0, and this is the displacement a, and this is minus a, okay? So near time equal to 0, notice that the slope is negative, okay? And it continues being negative, okay? So they might give you this plot and I'll ask you what the form of the velocity versus time graph looks like, okay? So you can safely infer that the velocity starts, since the displacement is at the maximum, the velocity is pi over 2 shifted with respect to the displacement. So you can safely say that it starts at 0, okay? And it's negative because of this negative slope, okay? So this is what the velocity looks like. Hope this makes sense. Now, how about the acceleration? The acceleration is going to be, remember that the acceleration is minus omega squared times x. So it's going to look exactly like the displacement graph, like this graph, with the sign reversed. What does that mean? That it will start at a negative acceleration. So it's going to look like this. Okay, so this is another thing to keep in mind. Okay, another thing I want to talk about is what is the form of the displacement function depending on where we start in the oscillation. This is something I mentioned but did not explain. So let's go. If the object is at the maximum displacement a at t equal to 0, then we use x equal to a cos omega ty, because at t equals 0, x equals a. If x is minus a at t equals 0, then x is naturally minus a cos omega t. Now, if x is 0, this is the case we studied, and object moves to the right, which means that it has a positive velocity, then x is a sine omega t. Why? Because at t equals 0, x is 0, and the velocity is the first derivative of x with respect to time, which is omega a cos omega t, and cos 0 is 1, so the velocity is maximum and to the right at t equals 0. And if x is 0 and the object moves to the left, meaning that it has a maximum velocity, because at the equilibrium position the velocity is maximum. So if it moves to the left, it means that x is minus a sine omega t. Okay, once you know the displacement, you can easily find the velocity as the first derivative of the displacement, and the acceleration as minus omega squared times x. Okay, so that's that. Let's do a small recap. X, the displacement in simple harmonic motion is sine omega t, and other cases studied. So we saw mainly a sine omega t, but we can also have a cos omega t, etc. The maximum displacement is a. The velocity is dx over dt, which is omega a cos omega t. And V max, the maximum velocity, is omega times a. And a is minus omega squared x, so minus omega squared a sine omega t, with a max being minus omega squared a. And before we close this video, I'm going to talk about some miscellaneous math. So miscellaneous math. So, for example, how can we find V for a random x? So x is not 0 or plus or minus a, which is the easy case, okay? So maybe x, so someone asks you what is the velocity of the object here, or here, or here. Not at the usual positions, which are this, or this, okay? And this. So this is easy. What happens at point x? So to find that, take x equal to a sine omega t. This demonstration works for any other function, but we're going to use this. And if x is a sine omega t, v is omega a cos omega t. Okay. And let's solve for the sine and the cosine. So sine omega t is x over a. Therefore, sine squared omega t, and you will see why I took the square, is x squared over a squared. And similarly, cos squared omega t is v squared over omega squared a squared. Okay, so if we add these two, we find x squared over a squared plus v squared over omega squared a squared is 1, because x sine squared x plus cos squared x is 1, and the same goes for any other sine and cosine function. So I'm trying to say sine squared omega t plus cos squared omega t is 1. Okay, so let's try to bring a squared to the other side. So x squared plus v squared over omega squared is a squared. So v squared over omega squared is a squared minus x squared, which means that v is plus or minus omega, and then the square root of a squared minus x squared. So if you know the displacement at some random location x, you can plug into this formula, and if you know omega and a, you can find the velocity. Okay. And for the sign plus or minus, you need to know about the graph. You need to know the graph. Also, last thing before I close this, stop this video, and there will be a second video discussing energy in simple harmonic motion and damping and stuff like that. But also don't forget another miscellaneous thing that we haven't mentioned, that don't forget that if they ask you for the force, so anything that they ask for the force, F on the object, then since F is m times a, which is equal to minus m omega squared x, then to calculate F or work with F, use F is equal to minus m omega squared a sine sine omega t. Yes, sorry, I got confused for a while. And F max is minus m omega squared a. So what I'm trying to say is that the force follows the same pattern as the acceleration, and to calculate the maximum force, you need to multiply with the mass of the object and get done with it. Okay, so this is the first part of discussing oscillations. There will be a second video. Hope you guys like these videos. Please let me know what you think about them in the comments, like and subscribe and all that things related to YouTube. So, so yes, I'm gonna stop the video here.